So, let us continue with the sensitivity analysis for min cost flow problems. I am considering the min cost flow and we are considering changes in UIJs. Okay, that means in the capacities. And let me, through the examples, I will try to explain and hopefully it should become clear. So, this was the example which I have also looked at earlier, and so the numbers we understand, these are the BIs, positive ones are the supplies, these are the demands, the negative ones, and then here the first number refers to the cost and the second number to the capacity of the arc, right. And then, yeah, so your sigma BIs must add up to 0. This is what our requirement is for the problem. And then I had obtained the optimal solution, which is shown here, and of course, little crowded, but does not matter. So, these numbers refer to your pi i's, right. So, for example, pi 6 here is 19. So, these values are the pi i's, the dual variables, and the square numbers denote the flow on the arc which are at their upper bound. So, these are non-basic arcs, the solid lines represent your tree, the optimal tree, and so here the flows, the circle numbers give you the flow on the basic arcs. So, this is what we have, and you can please verify that this is an optimal solution. Fine. Now, suppose I want to consider the change on 1 3. That means, right. So, the idea is that I want to increase the capacity of, see, for example, for yes, I should have mentioned that here. See, change in the capacity of a basic arc. For example, consider 3 2. The capacity is 35, but the flow on 3 2 is 15. So, increasing the capacity here will not change my current optimal solution, because the current, because even if I increase the capacity of 3 2 from say 35 to 40, the current flow will remain feasible, and since the optimality conditions are satisfied, there will be no change in the flow. This is the idea, right. So, therefore, I do not have to consider changes in the capacities of basic arcs which are at their not at their upper bounds, because you already have surplus of capacity. Similarly, for non-basic arcs which are at 0 level, for example, 2 5, there is no flow. So, this arc is not being utilized in the optimal solution, and increasing the capacity of 2 5 also will not matter, because my current flow will remain optimal, and therefore, I do not have to worry about it. So, we only need to consider arcs which are at their upper bounds, because for the non-basic arcs which are at their upper bound, the corresponding relative cost will be less than 0. And so, increasing the capacity, if I can also increase the flow on the arc and of course, conserve the flow in the network, then my cost will go down. So, it is worth considering the possibility that if I increase the capacity of a non-basic arc which is at its upper bound, will I be able to make use of that increased capacity and get and reduce the cost. So, I will go through the example and then I will point out what is the main issue here. So, for example, if U13, the arc for the arc 13, which is the non-basic arc at its upper bound, and its relative price is -7, which is less than 0. Right, because pi 0 is 0 and pi 3 is -9. So, you can compute, and the cost of arc 13 is 2. So, 2 minus 9 is -7, which is less than 0, and so delta 3. So, therefore, let me consider increasing the capacity of arc 13, say from 20 to 20 plus delta 13, right. So, that means I would like to flow delta 13 units on the arc 13, but if I do that, then I should be able to, because you see the demand here, the supply here has come down, because you have used delta 13, and the here the number now what is available is plus delta 13. So, I should be able to send flow delta 13 from 3 to 1 to balance to conserve the flows at each node, right. That is what we are doing. So, your conservation of equation. So, I mean flow conservation equations have to be satisfied. Okay. So, now here of course, when you, because you have a tree, you are adding this non-basic arc to the tree, then you will immediately have a cycle and consisting of the basic arcs. So, therefore, I can consider sending flow from here to here, 3 to 1. Right, and you see that, and then I will find out the path along which I can send the flow from 3 to 1, and then we will try to find out the capacity. So, for example, here I can reduce the flow by 20 units, and here also I can reduce the flow by 20 units. So, that means I can use this path, and so delta 1 3 units have to be sent from 3 to 1, and delta 1 3 comes out to be 20. So, my new optimal solution, you see I have diverted this flow along here and here to on the arc 1 3, and this gives me, I should have pointed out here that the reduction in cost is equal to minus 7 into 20, you see. So, because I have increased capacity available here, I could send 20 more units on the arc 1 3 and divert the flow on the arc 4 3 and 1 4 to the arc 1 3. So, this is the idea, right. And now, if you want to look at the possibility of increasing delta 1 3 further, that means I have made the capacity of arc 1 3 to be 40. Let us see if we can increase it further and get a reduction. So, that is not possible with respect to the current optimal solution, because you see that there is no path here now, and I am of course talking in a very ad hoc manner, and later on I will point out the right way to go about it. But in any case, see here, from here you can check that to send flow from 3 to 1, you have no possible path consisting of the current arcs, current basic feasible solution, right. And if you look at the cost of the cycle, for example, 1 3 2 1, this, because see here now this is 0 0. So, I cannot do anything with, I cannot use this particular path, because the flow from 4 to 3 is 0. So, I cannot go this way, I cannot reduce the flow. So, therefore, I have this possibility of considering 1 3 2 1, right. 1 3 2 1 is, but then the cost of this cycle, this if you add up is 2 plus 7 9, 9 minus 8 is 1. So, the cost of this cycle is 1, and therefore, the increase of 20 units is possible at the cost of rupees 20 additionally, right, because the cost of the cycle is 1. So, when I send 20 units along this per cycle, the cost will go up. So, it is possible, right, and if the current solution, with the current solution it is not possible. With the current solution I got a reduction of 140 in the cost. This is one. Then I will give you another example. So, now consider the arc 3 6. Consider the, again this is the non-basic arc at its upper bound here, right, and you see that C bar 3 6 is minus 5, which is less than 0. So, therefore, I can consider increasing the capacity of U 3 6. I mean increasing U 3 6. So, path from, so then if I increase the flow from 3 to 6, I have to divert that much flow from 6 to 3, right, and here you see this is the path, that means 6 5 7 2 3. This is the one along which you can send additional flow and I mean reroute the flow that you have used for this arc 3 6. So, here you can immediately see that the capacity of this path is governed by this number, because I can reduce the flow along the arc 6 5 by 5 units. I mean I can reduce the flow along 5 6, which means I can flow 5 units from 6 to 5. Okay. So, 5, and then of course, here the capacity will allow you to have 5 more here, because 5 7 the capacity is 30, and similarly I can reduce the flow by 5 units here, I can reduce the flow by 5 units here. So, therefore, my delta 3 6 can be path from 6 to 3 is this, and the capacity I am saying is 5, right. So, I can increase the flow on 3 6 by 5 units, and the reduction in the cost will be minus 5 into 5. Okay. So, a further increase in UT 3 6 is possible, again just as we talked about 1 3, but the cost will go up and the minimum. So, we will have to, so essentially what is happening is that when we want to increase the flow on 3 6, we also have to send flow, the same amount of flow from 6 to 3 to conserve the flow at each node, right. But then see, you want to know, and this is a small network, so we could simply find out what is the best route and so on. But when you want to talk of optimally increasing the flow on 3/6, that means optimally utilizing the increased capacity on 3/6, then you have to be able to reroute the flow in an optimal way, right. Now, there may be more than one path available from 6 to 3. Not the current, of course, the current tree there will be only one path which we used for increasing the capacity from 3 to 6. But if you further want to increase the capacity and you want to say what will be the minimum increase in the cost by doing that, then you have to find the minimum path, minimum rerouting path from 6 to 3 or from any for any pair of nodes I j that you consider. So, that will be require some work, and one would say that you have to find the path of minimum cost. I am calling it the augmenting path. So, you have to find the minimum cost path and then use that. So, we will have to do that, and later on I will also, after this I will be discussing max flow algorithms with you to finding the maximum flow. So, but that will not consider the cost. So, we will have to essentially find out the minimum costing augmenting paths when we want to increase the capacity, and so that will, of course, we have algorithms available for that, but right now in this course we have not considered that. So, what I am trying to say is that by increasing the capacity of certain arcs which are at their upper bounds, it is possible to reroute the flow and reduce the total cost of the flow. So, this is what we have actually investigated here as to how we can increase the capacity of certain arcs, and of course, we saw that that is possible only for arcs which are at their upper bounds, and then we can increase the flow on such arcs and reroute the current flow. So, that we get a better solution, that means a solution which has lower cost. So, we go on doing this sensitivity analysis, and of course, see in the earlier lecture I had talked about changing the values of the BIs, right, and we said there that if a particular supply went up, then some other demand must go down to balance the, that means we were considering the sigma BI to be 0, we have to maintain that. And here when we increase the capacity of a certain arc, then we want to increase the flow, then we have to make sure that flow is conserved at each node. And then doing that we can continue with the analysis as long as we want, and as I told you that after a certain point when you want to change the optimal solution, current optimal solution, then you have possibilities of how you do it, but the cost will go up, and of course, the question would be what is the best way to increase the flow, that means minimum increase you want to have in the total cost. So, max flow problem, and this is also part of your network flow problems. We have looked at the shortest path, min cost flow and so on. Transportation problem I looked at with you. So, all those were problems of allocation, right. So, this is another problem. So, here what we are saying is that you are given a network and you have a source node, a sink node, and these are your node set. This is your arc set, and then you have the capacities. Okay, so, no cost here. So, that means you simply have a source node and a sink node, then you have capacities on the arcs. You want to find out the maximum amount you can transport from S to T. So, in this case, for example, okay, so let me formulate the problem. This would be, for example, maximize V. Suppose I denote this as the amount of flow in the network. So, I want to maximize this, and then subject to this is my node arc incidence matrix, x is my flow vector, that means the component of x are the xij's, and xij will tell me how much flow is there on the arc ij. So, Ax, and I will explain this, this is 0, right, and then we want to say that x is less than or equal to u and x is greater than or equal to 0. So, they can only, and here when I write this, this means that D is plus 1 and 0. So, sorry, and this is minus 1, or should it be other way, right, minus 1 and plus 1. So, this is the sth row and this is the tth row. So, that means here if I write the constraint for the when I write the constraint for the source node, then actually what I am saying is that summation x s j, summation over j is equal to V, because you are sending the flow from node S. So, the total flow that you send from the node S is V, that will be the net flow in the network, because at every other node you are preserving your conservation of flow, because you see all other components are 0 here. So, this is not there, and then you are just wanting that whatever flow reaches a particular node, that should also leave it, right. So, therefore, if you are sending nodes flow V from node S, then all other nodes in between are working as transshipment nodes. So, no flow is remaining at any of these transshipment nodes, and then the final this thing is summation x j t minus this is equal to minus V. So, therefore, I am bringing this to this side. So, this becomes minus V equal to 0, and this becomes plus V equal to 0. So, the sth constraint and the th constraint, you will have a minus 1 and a plus 1, all other 0, right. So, this is, and therefore, you are wanting to maximize. So, you can say that this is also your min cost flow problem, where what will happen is that all your these BIs are zeros, these are your upper bound constraints. So, essentially your BIs are zeros, your CIJs are also 0, because I am not concerned with the cost, it is only the coefficient of V which is 1, otherwise this is the thing, right. Okay. Now, it depends on how I look at this problem, whether I call it a primal problem or a dual problem, but of course, so far our convention has been that maximization problem we treat as a dual problem. So, let us just look at this problem as a dual problem, and then let me show you what happens when I try to solve the problem by the primal dual algorithm, and there will be very interesting interpretation for this. So, I write this, and therefore, what I will do is I will write all the constraints as less, because this is maximization problem, dual problem. I am looking upon this as a dual problem, right. So, just rewrite this as less than or equal to 0, right. In that case, what would be your primal problem? So, here you see I can say that these are the nodes corresponding to the n nodes. So, let me denote the variables pi I, right, and then with these it will be Vij's, for Xij Vij, and for this Wij. So, right now I am not treating these as I am treating these as explicit constraints. Remember, in the linear programming formulation we were not worried about X non-negativity, these constraints, but here just to make the presentation simple I am doing this. So, therefore, so essentially this is minus Xij less than or equal to 0. So, this is the thing, right, and so what would be your this thing on the right hand side you have only non-zeros here, right, and the corresponding variables are Vij. So, this will actually become minimize summation you want to write Uij into Vij, right, and subject to, yeah, if you want to make life a little easy, I can rewrite here, see for example, this thing, yeah, okay, fine, yeah. So, subject to the matrix here, you see this is A I minus I, okay. If you look at the constraints, your matrix, that is what I was going to write here, this is A I minus I, and then you have D here, right, this is all zeros. So, this is your this thing, and you have here X and V. So, this is a singleton, this is the n dimensional this thing. So, this is what you have, right, and this is less than or equal to, you have 0, U and 0, and I am writing minus I because I am writing this as minus X less than or equal to 0, right. This is what you have. So, in the dual what will you have? The transpose of this, which will become A transpose I minus I, and then you will have D transpose 0 0, right. and so this will be, remember with this you have the variables pi, and with this you have the variables v, and then you have minus sorry w. So your, because constraints are less kind, so this will be what will you have? Yes. Now here I don't have any constraints on the sign of the variables, right, because I'm treating these as explicit constraints. So minus x less than or equal to 0. So v and x both are, the signs are not specified, so therefore this will become 0. Yes, well, why should I say 2? Sorry, this will be 2, right. But you had non-negativity here, so therefore your v and w's are v and w are greater than or equal to 0. Is it okay? Because these constraints are less kind. This is equality, so your pi's are unrestricted, but your v's and w's are restricted. Okay, fine. So this, that means this actually becomes minimize summation uij vij. I should have said ij belonging to A. So this is also ij belonging to A, and this becomes A transpose pi plus V minus W equal to 0. There should have been for the D, you see for the V1, this thing is 1, because the coefficient here is 1, right. Okay. So we have that D transpose pi is equal to 1. So this actually, this constraint is simply this, this is equivalent to, because remember this is minus 1 and plus 1. So this is minus ys, or okay, pi s plus pi t equal to 1. Okay. So this is your primal problem, right, and that is my dual problem. So now when you have this dual problem, here you will define your set ij. So tight dual constraints, index set ij. So I'll define, okay, so ij will be all arcs ij for which either xij is uij or xij is 0. Okay. So these are the only possible, because the other set of constraints are all equality constraints. This is, remember, flow conservation equations. So either xij is uij or xij is 0, right. So then when you want to define your restricted primal, yeah, I hope you enjoy this exercise, because I am trying to show you something here, and this is restricted primal. See, you have to add artificial variable here, you have to add an artificial variable here, right, and you will only consider because here you are considering the columns ij which are in capital Ij. That means a corresponding row constraint here would be considered, right. So you will write restricted primal would be minimize now xij ia summation ij belonging to A plus, let me write V bar A corresponding to this constraint, yeah, the dual artificial dual variable. So V bar A, and therefore and subject to, so this will be A transpose pi plus V minus W plus, we are writing x, okay, x A, right, is equal to 0. So I am just calling this vector comprising of all the ij's as this, and then you have this also I can write in the simpler form, which is minus pi s plus pi t plus V bar A is equal to 1. Yes, and you have the non-negativity signs about xij A greater than or equal to 0 for all ij. Remember, because we want to minimize this thing, and V bar A is greater than or equal to 0. Fine. And this is for ij, remember these belonging to capital Ij. So, the ones for which are the ij's for which the constraints are tight, the dual constraints. So, that means I have a starting flow, I have a starting flow in the network, feasible flow, because any x satisfying these constraints represents a feasible flow in the network. Okay. So, then correspondingly I then find out the tight constraints, and corresponding to that flow, then I am saying that now you want to look at the restricted primal. So, this would actually be, I said restricted, this would become restricted dual. Oh, okay, okay, hold on. Where I call this as the primal, so that was the dual. Okay. So, now write the restricted dual problem. So, yeah, earlier I have been simply writing dr, but I think it is better to say that the dual of the restricted primal. So, the whole thing drp is the better nomination for this thing. I have been writing dr. So, anyway, I meant it was dual of the restricted primal. So, what would be the dual of the restricted primal now? Yeah, this is this was oh, by the way, here I should not have written here. So, this was xij, and I could have written something else here, but let us see. Okay. So, anyway, I will try to write. So, this will be maximize. Yeah. So, let us write the restricted dual now. So, so therefore, the transpose of this. So, actually now what does this matrix become? This is right now A transpose I minus I and I again, right, because this is whole set of this thing, this, and then you have a D transpose, and we have a 1 here, right, where it is a 0. So, this is 1, and this is all 0, 0, 0, right. So, this is what you have, and this is this was our pi v w x a, and I was writing v bar a, okay, because 2, 4 and 5. So, 3 and 2, 5. So, that many you should have, fine. And now you want to write the dual. So, therefore, what will happen? This will become a d, then this will be I minus I 0, and this will be 0, 0, 0, 1, right. And then let me write use some other this thing, okay, f. Let me write f as the vector corresponding to, so the flow, the corresponding to x. I could either use y or f, does not matter, f you will have here, okay. And we will have a corresponding, yeah, I should not have used the symbol v bar a here. Let me write something else here, okay, fine, or maybe we will do this thing here, something like w bar, okay, this, right. And so, maximize, you are maximizing w bar here, right. If you want to write a, write it this way. That is the only one which has a one coefficient here, right, corresponding w bar a I am writing for this the variable. So, therefore, that will become max that, and so the coefficient is 1, and here your constraints will be all less than or equal to, yes, because remember we were writing all constraints less than or equal to kind except for this one. So, maybe you can say that this is all 0, and then here this is also, yes. Now, what are the coefficients? See, now the coefficients here, this is are all 1s. So, for these two it becomes 0, 0, because your v and w are not present here in the objective function. It is only the artificial variables which are present. So, corresponding to those, this is my I here, and so this will become E, right, all 1s, and this is 1. So, these are your dual constraints, and you can correspondingly have your. So, therefore, and so here again, because this was all yes, okay. What would be writing here in the minimization problem? Remember, I had all equality constraints. Okay. So, therefore, this was your no restrictions on F and W bar A, right. Okay. Now, I want you to look at this set of constraints, this problem very carefully. See, the first one says that your AF plus D W bar A is 0, which is your flow conservations, which we are anyway having here, and this is, remember, only for rest, and then it will tell you F less than or equal to 0. So, Fij less than or equal to 0, and remember this corresponded to your V's, and then we said that here for the tight constraints, since we in the restricted primal we went back to, we said that here you can only have the corresponding constraints which are tight for the dual. So, the Vij Fij is less than 0 when Xij is Uij, right. See, this is your Ij. So, here the columns for corresponding you are considering the columns for which Xij is Uij or Xij is 0. So, in the dual thing it will become the row, and so you are considering only those Fij's for which Xij is Uij, and the second set is minus Fij less than or equal to 0 when Xij is 0. Okay. Then you are saying from here that your Fij's will be less than or equal to 1 for all Ij belonging to Ij, okay. Fij less than or equal to 1, and then the final constraint is that W bar A is less than or equal to 1. See, what I will suggest is that sit down, go through all this formulation very carefully, right. So, finally, this is the dual of the restricted primal, and see what is happening here. You are saying maximize W bar A is less than or equal to 1. Then it is saying that for arcs which are saturated in the current flow, okay, Xij is equal to Uij, you can reduce the flow, and so you are trying to find out Fij less than or equal to 1, and for arcs which are not saturated, which have no flow, which have 0 flow, I can increase the flow on those arcs, and so my Fij is greater than or equal to 0. So, essentially the restricted dual problem, and my idea of spending so much time on this is just to show you that the primal dual algorithm finds applications, because you can show how useful it is, because here I am trying to give you another interpretation of the primal dual algorithm, and which is showing you that the restricted dual is actually nothing but a reachability problem, because you are saying that your Fij's have to be less than or equal to 1, you have conservation of flow. So, essentially here, if I let me write it somewhere here, yeah, I do not need this anymore. So, now as I was showing you that this is my DRP, and the DRP actually now reduces to a reachability problem. DRP is a reachability problem from S to T. See, if I have an arc here, say for example, if this my node S is here, right, either I have an arc like from S actually we are not having arcs like this. So, if there is an arc with no flow on it, that means currently the Xij is 0, then I can increase the flow on it, right. But the idea is the flow has to be of 1 unit. That is why I am calling it a reachability problem, because we are just looking for a path. So, this is so that if there is an arc like this, then I can use it, right, because I am trying to solve this DRP, and the solution would be that, and then from there I will again try to see if there is an arc here on which if you have a flow in this direction, then I can reduce the flow, or if it is again no flow on it, then I can increase the flow, and this way you see just using arcs, I will use the arcs in the forward direction for which there is no flow currently on in the network, and arcs which have saturated, I will use them in a backward way, and this way if I can continue finding, and I will maintain conservation of flow, right, and then the maximum if I reach T. So, finally, if I manage to reach T by these arcs, then that means my W bar A will be 1, because here you see this is less than or equal to 1, you are trying to maximize it, right, and all these constraints will be satisfied. Here also you see that these constraints will be satisfied when I choose W bar A less than or equal to 1. So, this will be my optimal solution. So, that means the optimal solution for DRP is finding a path. This is finding and augmenting path. So, augmenting path, that means you are augmenting path from S to T. So, once I find an augmenting path from S to T, then see I have now I know that I can increase the flow on the arc on this augmenting path. So, find the capacity of this augmenting path. I had explained to you earlier, find the capacity of this augmenting path. See, we discussed this while looking at the changes in BIs, and I told you that the capacity of a path is the minimum of the capacities of the arcs that make up the path. So, find the capacity of this augmenting path and increase the flow on this path by that amount. So, by the capacity on this path by the maximum possible amount, right. So, I find the capacity. So, therefore, the restricted dual problem is actually finding an augmenting path if one exists, and then I increase the flow. So, we can see that the structure of the algorithm that we will use, and this is again a simplification of the simplex algorithm and plus the primal dual this thing. So, we are basically using primal dual pivots to find augmenting paths. Then you find out the capacity of the augmenting path, increase the flow, you update your dual solution, and then you will have your new IJ, right, and then you will again define a restricted problem, dual restricted problem, and then you will try to find an augmenting path. So, you will go on doing this till, because your objective is to maximize the flow in the network. So, you will go on doing this till you cannot find an augmenting path. So, essentially this is the basic algorithm. There are some refinements. So, we will later on discuss the algorithm, how to actually, without actually doing all this, we will simply try to find augmenting paths and augment the flow by as much as we can. Okay. So, that is the basic, but the idea here was to show you that the origin of all these algorithms are through the linear programming theory, and that makes it very interesting, and you see how it is so versatile. Okay. Yes, so now we can again just try to look at the some more theory. So, I need to develop, because I have to show you that here, even though we are using the primal dual pivots, I am not maintaining basic feasible solutions and so on. So, we need to essentially finally prove that the algorithm will be finite and that we will get an optimal solution here. So, all those things have to be done. So, if I just simply yes, let me reformulate the problem. Now, I will write the max problem again as max V subject to Ax plus dV equal to 0 and 0 less than or equal to x less than or equal to u. I will simply look at this, or okay, you want to do this, and then this we will now not treat explicitly. So, I will come back to the usual thing, right, fine. So, this is your this, and therefore, dual or if I mean you can keep calling this as the dual or the primal, does not matter. As I told you that the dual of the dual is the primal, so it does not matter. So, dual would be minimize, as we said, this is summation uij vij subject to, and remember this I will now write in pi I minus pi j plus Vij. Yes, because a column here will have two entries plus 1 minus 1 and then Uij plus Vij. This will be, because now I am taking non-negativity constraint. So, this will be less than or equal to, or sorry, greater than or equal to 0, greater than or equal to 0, and then you will have minus pi s plus pi t, right. Okay. So, that is it. This is equal to, because my V is unrestricted. So, this is equal to 1, fine, and you have your Vij greater than or equal to 0. So, I am keeping it this more simplified, because I am now not treating these constraints as explicit constraints. Okay, fine. So, now I want to show you that a dual feasible solution, I can look upon the this thing as representing cuts. Now, I introduced to you the idea of cuts, which is the partition of the node set, and then S belongs to. Therefore, I said that in this particular case, SS bar is a cut such that S intersection S bar is empty and S union S bar is V, and we are considering particular cuts where S belongs to S and T belongs to S bar. So, now because we are trying to send flow from S to T, so this is what is it. So, now let me define a dual feasible solution. Dual feasible solution where I say that pi I is 0 if I belongs to S is equal to 1 if I belongs to S bar, okay, and Vij is 1 if I belongs to S and J belongs to S bar, 0 otherwise. Okay. So, look at this dual and I claim that this is a dual feasible solution. Why? Because see, these are your variables, right, and so here quickly check for feasibility. What are the possible situations? Ij both belong to S. If you have Ij both belonging to S, then you have a constraint like this, pi I pi j both are 0, Vij is 0. So, this is satisfied, right, and here this is 0, this is 1. So, this is satisfied, you are done, right, and Vij's are non-negative. Then if I and j both belong to S bar, then also both are 1. So, this is 0, this is 0, again this is satisfied, this will continue to be satisfied because S is in small s and T is in cap S bar, and this is satisfied, right. Then you have the case I belongs to S and J belongs to S bar. I belongs to S and J belongs to S bar. So, then pi I is 0, pi j is 1, so minus 1, but Vij is 1. So, again the sum is 0, and so this constraint is satisfied, this will continue to be satisfied, this is non-negative. Then the final case you can have that when I belongs to S bar and J belongs to S, you can also verify. So, therefore, what we are saying is that the dual solution, the feasible solutions are, there may be many more other solutions, I am not denying that, but essentially but basically all cuts are feasible solutions here, and therefore, and if you want to define, and of course, I am going to talk about cuts some more later on, because we will spend some more time, but right now you can just immediately see from the duality theory, we see that because this is a minimization problem and that is a maximization problem. So, if you say that capacity, because if I take a feasible solution, a cut as a feasible solution, then what is this? The objective function value is simply adding up, because my Vij's are 1 only when I is in S and J is in S bar, right. So, that means what we are saying is that capacity of S bar is summation Uij I belonging to S and J belonging to S bar, right, because you have this is S, this is S bar, you have like this with uij. So, we are saying this. So, that will be the objective function value for this dual feasible solution, and by duality theory, of LPP, you have that capacity of a cut is greater than or equal to the flow in the graph, in the network, in the flow in the network. Okay. And we will further discuss and look at very interesting aspects of this thing. But first of all, we have said that the capacity of a cut will always exceed the flow in the network. So, let me discuss assignment 7 with you, which was long overdue, but we had just finished discussing the sensitivity analysis for min cost flow problem. So, I thought I will give you a few problems to work on the min cost flow problem. So, the first problem is simply I have given you an uncapacitated min cost flow problem, and you can easily transform it to a transportation problem. Remember, finding out the shortest path between every pair of supply and node and demand point, and then you can solve it as a transportation problem. So, that is your first problem. Okay, then go to second problem, which is, now what am I asking you to do here? Yes, this is the min cost flow problem given below with positive lower bounds. We had not discussed, or I had mentioned to you how to take care of lower bounds if you have, because we were all the time taking lower bounds to be zeros. But now here you see, for example, from 1 to 2, the flow, there is a lower bound of unit 1. That means you must, in any feasible flow, send 1 unit of flow from 1 to 2. Okay. So, that means what? That means, so the idea here is, and I have given you, explained to you through a note down below, below this problem. So, I am suggesting to you that the lower bounds, since you have to send that much flow, you just send that flow on the arc. So, for example, I will flow 1 unit of flow on 1 to 2, and then I will increase the decrease the supply at node 1 by 1. That means, the new supply will become 2 units, and the demand at node 2 will become -1. Similarly, you have this thing here, the lower bound from 4 to 5 is 1 unit on the arc 4, 5. So, here I will reduce the supply, that means, or in this case, of course, it is the demand. So, the demand will become -2, and because I am sending 1 unit to 5. So, the supply at 5 will become 3. This is the idea. So, once you do this, then the new problem you can solve as a min cost flow problem with 0 lower bounds. So, that is the idea, because our algorithm we have designed it for lower bounds being zeros. One can do it, one can modify it, but then it becomes very cumbersome. So, this is what I have explained to you here. Okay, since I am sending, so what I am saying here is that I am sending 1 unit from, okay. So, B4 will actually become -4, right, and B5 will become 3, that is right. So, that is okay, because you must have conservation of flow, and since B5 is going to increase by 1, B4 must reduce by 1, otherwise the sum of the BIs will not remain 0. So, right, I should not have said. So, this is B4 will become -4 and B5 will become 3. Now, problem 3 showing you this min cost flow problem, which I had worked out in the 29th lecture. Then the optimal solution I am showing you in the next network. Fine, this is your this, and then I am asking you, yes. So, now there are a few problems that I am asking you to look at, and so this is sensitivity analysis or post optimality analysis. So, I am saying that by how much can C12 and C35 change one at a time, so that the current solution, yeah. So, with respect to this network, you are going to now answer these questions. By how much can C12 and C35 change one at a time, so that the current solution remains optimal. Now, 1, 2 according to, we will have to go back to the diagram here. 1, 2 is a non-basic arc at its upper bound. So, currently its C12 bar is less than 0, right. And so, I am asking you to, by how much can it change, so that the current solution remains optimal. yes, and so I am saying that suppose it goes up by delta 1 2, then you have the inequality C12 plus delta 12 minus W1 plus W2 should be less than or equal to 0. It should remain non-basic, and the optimality criteria should not be violated. And C35 is what? 35 is a basic arc. So here once it goes up by delta 35, then remember the other nodes, the other node potentials will also change, and so you may get an interval for delta 35 within which, if your delta 35 varies, then your current solution will remain optimal, right? And then you know how to. So then again in the problem 2, I am asking you for 25. 25 is also a basic arc, and I am saying that here this changes by delta 25, and again I am asking you to find an interval. So what is happening? 35 is also basic, yeah. So again I am asking you to do it for 25 also. 25 is a basic arc, and I am asking you to find out the interval for delta 25, so that the current solution remains optimal, right? Then part 3, I have changed B1 to B1 plus delta, that is and B4 to minus delta, because B4 was a transshipment point early. Since so that the sigma Bi sum remains 0. So now here find an interval for delta such that the current solution remains optimal. So just what will be the feasible values of delta, so that your current solution remains optimal. So therefore you have to try to send along the path from 1 to 4. You will have a path in the spanning tree, current spanning tree, and just see how much amount you can send on that path, and that will be your feasible interval for delta. Okay, in 4 I am saying that B1 hat has changed to 25 plus delta, and B2 hat is minus delta. In this case also determine an interval for delta so that the current solution remains optimal. Then I am asking you show one iteration of the dual simplex algorithm when delta exceeds either of its limits in 4. So here now I want you to consider changes in delta beyond this feasible interval, and then you will have to use the dual simplex pivot to find out a new optimal solution. Okay. Then the part 5, which I just discussed with you, relates to change in the capacity values. So U12 is a non-basic arc, and I am saying that the capacity goes up to 20. So the current capacity may be, check whatever it is, and since C bar 12 is less than 0, I am reminding you again that the increase of flow on arc 12 will improve the cost. Thus the current solution may no longer be optimal. Obtain the new optimal solution. So the new optimal solution, yeah, we don't know by how much. I think the capacity for, okay, let's just verify. For C12, for arc 12, the capacity is 15. So if I am raising it to 20, then we have to see, can we by sending 5 more units on the arc 12, can I send the 5 more units from 2 to 1? That's what I have to find out, right? And then that will be feasible. If I can, that means the capacity of the path 2 to 1, and which is in your current optimal solution, the path is from 2 to 1 is 2, 5, 3, 1, and you see that the blocking arc is 3, 5, because there is no positive flow on 3, 5. Therefore, I cannot reduce the flow and so the capacity of the path 2 to 1 is 0. So therefore, the current solution will not remain optimal if you increase the capacity of the arc 12, and so you will have to then drop the blocking arc, then in the cut find the eligible arcs, and from among the eligible arcs choose the one which has the lowest relative cost and increase the flow, and see if you can increase the flow by 5 units. If not, then again you will find a blocking arc and again find a new eligible arc, and so on. So you will continue with that. So I wanted you to work out the details what we discussed in the lecture. So that takes care of your, and then arc 25 is a basic arc. Yeah, so what am I just finished last part. Arc 25 is a basic arc at its upper bound. Suppose U25 decreases to 10. This I have not discussed in that lecture, but now you can surely, you have all the tools to handle this problem also. So now U25 is decreased to 10. So the current solution is no longer feasible. Obtain an optimal solution using the dual simplex pivot on the current optimal because the current solution has become infeasible, and so see if you can handle this part also. Okay. So, hope you will enjoy doing this assignment sheet.